Okay, so a standing wave is actually just an interference pattern, which is why we teach this lesson after we go over interference. Okay? So if I start making waves, okay, and they go towards Emma, they will reflect off of her, okay, inverted, not because she's dense, but because she's a fixed end. Okay, talked about that the other day. You weren't here when we talked about that. Okay, and so I would get this pattern here. Okay, this is my first and simplest standing wave pattern. Right? Always looks the same. Okay, what kind of interference is happening in the middle? Constructive, because look how much I'm moving my hand. Okay, I'm not moving my hand nearly as much as that spring is moving in the middle. Okay, I'm not putting that much energy into each wave, but every time one of those waves hits Emma's hand, it reflects back. So all that wave energy is staying on the spring. And it always, because I'm shaking it at a constant frequency, I'm always making waves of the same wavelength. Because they're on this spring and I'm not changing the spring, they're all traveling at the same speed. Okay? So they're always going to interfere with each other at the same spot. They're going to create destructive interference at Emma's hand, destructive interference at my hand, and constructive interference in the middle. Okay? Why is there always destructive interference at Emma's hand? When a wave hits a fixed end, it reflects inverted. So it's always creating its exact opposite at her hand. That's why it's always destructive interference at her hand. Okay, same with mine. So the waves I'm making are traveling back and forth multiple times. Okay, everybody all right with that idea? Okay, this is the simplest wave pattern. I'm probably shaking this at a frequency of about 1 hertz, maybe 2 hertz, I don't know, something like that. Let's say it's 2 hertz, just for argument's sake. Okay, what would happen if I shake this at 4 hertz? Yeah, I'll get 2 hertz. Okay, again, I'm not moving my hand as much as the spring is moving. Okay, but I've made enough waves that there's wave energy, okay, staying on the spring, it's reflecting back and forth, it's interfering with the new waves that I produce, and I've got now 2 areas of constructive interference and 3 areas of destructive. Where's the third one? In the middle. Okay, so we call them standing waves because the pattern stands still. Okay, how many wavelengths are on the string right now, or the spring right now? 1. Yeah. Okay, we've got 1 up and 1 down. Okay, there's 1 wavelength on the string right now. Okay, you're gonna have to hold it as still as you can, because as I start getting faster, it gets harder to hold. It starts behaving like you're trying to hold a snake. Okay. Okay, now I'm shaking it at about 6 hertz. Okay, and it wants to rotate. Get kind of close to the smartboard. Okay, so I got 3. Okay. Give it a chance to settle down here, and then I'll try and get 4. I can't go any faster than that. Okay, does that make sense? All right, so I get that standing wave. Thank you, Emma. Okay, on the spring, right, just a pattern of interference going back and forth. Now, standing waves have a lot of uses and a lot of drawbacks. They are very useful in music. Any musical instrument produces a standing wave. Whether it's a string instrument or a wind instrument, it is producing a standing wave. It's either in an air column or it's on the string itself. It's a string instrument. Okay. There are some places, though, where we don't want standing waves. Where would some places be that we wouldn't want standing waves to occur?
A microwave.
Well, actually, in a microwave, yeah, if you put like metal inside and it reflects the waves back, yeah, that's bad. I don't know if it's necessarily a standing wave, it's more the reflecting wave energy just coming back.
A TV, you wouldn't want standing waves, right?
Trying to think how you get standing waves in a TV, especially now when they're LED.
Yeah.
Yeah. You might have in an old CRT, one of those ones that had a tube. They actually did use waves, electrons, and things like that to produce the picture. Where else would you not want a standing wave?
Radio.
Actually, a radio uses them. So it's a place where we would want them both as the signal is coming and also in producing the sound. Any structure, you don't want a standing wave to form in a structure. Okay? All structures are designed to move a little bit, to flex a little bit, believe it or not. Skyscrapers, bridges, okay? They're all designed to flex, just a little. Because if they don't, the slightest little bit of thing can get them to collapse, okay? Get them to fall. But at the same time, I don't want waves to be able to travel from one end of a bridge to the other and keep going back and forth. Because if those waves can go back and forth and more waves are created, and I get a standing wave pattern on the bridge, what's the bridge going to do?
Eventually.
It's going to do this. I know right now you're thinking there's no way any bridge could do that. It took years, I think it was like 30 or 40 years, before they figured out why the bridge actually did that. So what they found was that as the wind was blowing this way on the bridge, okay, what would happen was this side would lift because the wind would be pushing on it. And then as the wind hit it, it would curl like this because the bridge would slow it down. And when it curled around the other side, it created a vacuum or a low pressure area on the other side of the bridge. So you've got a force on this side of the bridge and then like a suction on this side of the bridge pulling down, this side pushing up. And so once the bridge started to get that happening constantly, it got a standing wave in it. The bridge was designed to do this. It was designed to oscillate up and down. Okay? It was actually built, okay, to withstand a lot of actually movement this way. But it was never designed to torque and twist because no one ever foresaw that that action could actually build up. Okay? They built scale models of this thing, put it in the wind tunnel, okay? And they just couldn't figure out why it kept doing that until one of the guys who was one of the engineers, because this is way back in the day, he was smoking in the wind tunnel, and the smoke from his cigar went through, and you could actually see as it passed over the bridge, it went, and it created that little vortex that sucked it under the other side of the bridge. And they're like, oh, okay, so this side of the bridge is being pulled down, this side of the bridge is being pushed up, okay? And that's gonna keep happening. You're gonna get that torquing, twisting wave. Okay? So obviously, we don't want standing waves to be set up in a structure. Skyscrapers downtown Calgary, we have to build them to withstand strong winds. Okay? So they're actually designed to flex and sway, just a little. Okay? Sometimes people can actually feel that. Okay? My wife used to work in Bankers Hall, okay, way back when near the top, and on really windy days, she could feel it, and there were some people that would have to go home because they would get nauseous, seasick from the movement at the top of those towers because they're designed to flex. If they weren't designed to flex, the wind would blow them over. Okay? So they're designed to flex a little bit. But the solution to not getting a standing wave is to use what we know of waves. The reason the standing wave got on that structure was because waves could travel on both sides of the bridge at the same speed. And so they would have the same wavelength and the same frequency, and then I'd get a standing wave pattern set up. All you have to do is make the tension in the cables on one side of the bridge different from the other. Then you change the speed at which the waves can travel on both sides of the bridge. Now you can never get a standing wave pattern set up because the waves will never ever meet at the same point and interfere constructively or destructively. That sort of makes sense? Okay? They do the same thing with buildings, okay, especially in earthquake-prone areas. On the four corners of the buildings, their pilings are basically like big giant shock absorbers, and they all have a different spring constant. So that when the building starts to sway, it's not when it reflects off the bottom and goes back to the top and reflects off the top, it's traveling at different speeds on the different sides of the building, so you can't get it to sway very much. Okay. So there's a lot of engineering about waves that goes into construction, especially in windy and earthquake-prone areas. All right, so standing waves result from repeating patterns of interference. Okay, and we've looked at how those patterns are formed. Okay, we just have waves going back and forth, and because they're all the same speed, all the same frequency, all the same wavelength, they always meet at the same places. All right, and so we're going to look at the names here of those different spots on the wave. Okay, so these are basically the standing waves that I showed you on the spring earlier. This is our first standing wave pattern. Okay, so we call it F1, or the fundamental frequency. Okay, sometimes we also call it the first harmonic. Okay, and then this one here is F2, and it is our second harmonic. And then this one's F3, our third harmonic. Okay, if F1 is 10 hertz, what's the frequency for F2? If I want to make what I've done is I've cut my wavelength in half, right? If I'm cutting my wavelength in half, did I have to shake the spring faster or slower? Faster, right? This here was the slowest one. It's 10 hertz. This one must
sorry, I
be-
thought you were saying to get to the, yeah.
Oh, no, yeah.
Yeah.
So if this one was 10 hertz, this one is 20, and this one is 30. Okay, this is how you make musical octaves. Okay, on a string instrument at least. Okay, so if you've got like, you know, middle C, the next C up is the next harmonic of that frequency. So on that string instrument, like if it was a piano, that string would be shorter, half as long, okay, to produce the next octave. All right, everybody okay with those terms? All right, this area here of constructive interference, constructive, those are all called antinodes. Okay? They are the areas of maximum displacement and constructive interference. And then these areas here, okay, those are destructive interference and they are nodes. Okay, everybody all right with the standing wave stuff? Okay. Okay, so I've got them labeled here as well. Okay, nodes are places of destructive interference, antinodes are places of constructive interference. If this was a sound wave, what would I hear at a node? Nothing, yeah. There'd be no displacement, there'd be no amplitude, that would be a point of silence. Whereas at an antinode I would hear a loud sound, yeah. Okay. All right, and then we have our antinodes, okay, and that's kind of the diagram I was showing you there a minute ago. Okay, our first harmonic is our fundamental frequency, and the wavelength is 2 times the length of the medium, because how many wavelengths are on there? A half a wavelength, right? A full wavelength is this one here, right? We can actually see that in the dark black, which I'm now making red. Okay, on this one, okay, on our second harmonic, okay, we don't use the overtones, so don't worry about those. Okay, and our second harmonic, okay, the wavelength is the length of the string, okay, because I can get one wavelength on that spring. Here I only get half an oscillation. If I had another oscillation, it'd be way over there. Okay, and then on this one here, on the third harmonic, okay, I get 1.5 wavelengths, okay, on there, and then in the fourth harmonic, I can get 2 wavelengths on the string. Okay. Everybody okay with that? Okay, right, and then we talked about this as well. Okay, if F1 is 10 hertz, then the frequency needed to establish the 2-loop pattern is 20 hertz, to establish 3 loops, 30 hertz, and so on and so on. Okay, the frequencies are called harmonics. We don't call them overtones. Okay, some books will use the term overtone, but we find that confusing because when we say first harmonic, there's 1 antinode. Second harmonic, there's 2 antinodes. Third harmonic, there's 3 antinodes. It just makes more sense. When we use second overtone and third overtone, the numbers don't match up, so we don't use those. Okay, so we'll only use fourth harmonic, fundamental, okay, things like that.
The overtones just be how many nodes it was in it?
No, because there's actually 3 nodes in the first overtone. One here, one here, one there, yeah. So we just find that that's confusing. People get it messed up with the number. The harmonics match nicely, makes more sense. Okay, and yeah, so we have identical waves traveling back and forth on the spring. And you can actually see that when I was trying to get some of those faster ones set up, that I struggled a little bit to get them going. Because if I don't move my hand perfectly up and down with the same frequency, I get a couple of waves that don't match up and they create a jumbled mess. Okay? So I have to make sure that I'm going at the right frequency, and the faster that goes, the more the margin for error becomes. Okay? And it's harder to get that spring to show the shape. Okay? So a standing wave is said to be standing because it does not travel in one direction or the other, okay? But the waves that produce it do. They go to one end, they reflect off, they come back, okay? And they keep bouncing back and forth, which is why we can get those massive displacements, okay, or amplitudes in the middle, even though we're only moving our hand a little bit. And we're not putting that much wave energy in each time, but that wave energy stays on the spring, so they get bigger and bigger. Okay, and then we talked here about this actually when Emma was holding the other end. Okay, I said that the reason we have a node at each end is because the waves are always producing their exact opposite when they reflect off of that, because they reflect back inverted, so there's always going to be a node at each end. Okay, and so this is how we make different musical notes, obviously on a string instrument. Okay, if I use the full wavelength, okay, of the full length of the bridge. Is that what it's called? Yeah?
It's called the neck.
The neck? Okay. So if I use the full length of the neck, okay, let's say it's 60 centimeters long, okay, what would my wavelength be for that wave pattern? How many waves are there? Half. So my full wavelength isn't 0.6, it's 1.2. Okay, so I know my wavelength is 1.2. Okay, and that's going to produce a frequency of 165 hertz, probably a speed of 340 meters per second for the speed of sound. Okay, if I pinch the strings here, okay, on the neck instead, then this part of the string doesn't vibrate. And I produce a much higher frequency of sound because now the wavelength is only 0.6 meters instead of 1.2, right? So I'm going to get twice the frequency, okay, because I've now got a shorter length of string that is vibrating, right? The speed is staying the same because we're still talking about air. Okay, everybody all right with that idea? We're going to talk about air columns, start a class on Monday. We gained it back a little bit of time here. Okay. Good.